Okay, but Fourier spectroscopy today, so what I'll do is I'll explain the basic principles behind pulsed Fourier spectroscopy. As you probably know even from school, in the old days the spectrometers worked by just trying every frequency in turn, or every wavelength of the light in turn. They looked in the following way. There was a source of light which shone onto a sample. The sample absorbed some of that light, and there was a detector here that detected it somehow and then plotted it against the wavelength of the light. And so through a sequence perhaps of monochromators, very precise selection of wavelengths was possible, or through tuned electronic circuits, very precise selection of radio frequencies. And so what we would plot eventually is the absorption of the sample against the wavelengths or the frequency of whatever radiation it is that's actually hitting it. And then we would see a series of peaks, which would be very sharp peaks in nuclear magnetic resonance and EPR, rather broad peaks in infrared, even broader peaks in optical absorption, but ultimately what happens is the sample absorbs light and we are detecting it. Right, so I will move to a seemingly unrelated picture now, but which, that picture we will relate directly to this one in a moment because it underpins the mathematical formalisms that we're about to start using. Consider the problem of tuning a bell. Yeah, we have a bell suspended on some support, and we would like it to have some frequencies but not other frequencies. It is possible to a limited degree to predict what frequencies this bell is going to resonate on from just its shape, but ultimately there's a problem of final tuning of it. So what can we do? We can do acoustic spectroscopy. We can shine on it the acoustic waves of different wavelengths. So we would have a speaker here, which would just give out sound, and we would have a microphone here, which would record the sound once it has passed by the bell. At some frequencies, clearly the bell would resonate. So the mechanical motion of the resonating bell, because of the conservation of energy, would result in the absorption of the energy from the acoustic field. And so at some point in the frequencies we would register an absorption. But this would be a rather slow process. Yeah, we would have to start in the infra waves, somewhere sort of 20 Hertz or so, and then scan it slowly all the way to 20 kilohertz, and then by removing material from that bell, try and get this spectrum to the shape that we require. An alternative way of doing the same, as most bell tuners in practice would of course know, is they just need to hit the bell with a hammer. Pretty hard, and the bell will start sounding. Now it is intuitively perhaps clear at this point that the frequencies that will come out of the bell once we hit it with a hammer would be the same as the frequencies that the bell is resonating. But what we will be busy doing today is figuring out the mathematical relationship between these two pictures. Now the great advantage of such a picture is twofold. First of all, the process is much faster. Smack it with a hammer, you record the ringback, that will take a couple of seconds, whereas the original scan would have taken considerably longer. Second, there are limits to how much acoustic power the speaker can actually put out. The microphone would have to cope with a lot of sound that just passes straight through, whereas here we can very easily control the strength of the strike. The stronger we strike, the greater will be the signal of the microphone. All of that signal would be relevant, and so we have two key advantages potentially to this method over that. Is first, it takes a lot less time to perform this experiment, and B, we potentially get much greater sensitivity out of it by doing it this way. And this, in fact, is the relationship between the classical slow path magnetic resonance spectroscopy, where we treat every frequency in turn, and the pulsed magnetic resonance spectroscopy, when we hit the system with a hammer, then record the ringback, and in the ringback, as you know, and as we will prove today, the frequencies are related to their corresponding oscillations in the time domain by the Fourier transform. Okay, so that was the setting for today. Now let's move to mathematics, and this course will be really heavy in mathematics. So if you've got any questions, just come and ask. You know where my office is. It's rather inadvisable to fall behind on that math. So if you feel like the lecture was at a level above, just find me and I'll explain it to you, because by about lecture 20 we will be in such deep waters mathematically that it's quite essential that you understand the full chain that has led up to that. Okay, so mathematically speaking, what we will be dealing with today is called a linear time invariant system, LTI. And we will make it a black box which accepts an input, x of t, some time dependent signal, and gives us an output, y of t, which is also some time dependent signal. And the two things that we need to know about this system are the so-called linearity conditions. That is, if we take our system and we feed into it a linear combination of the signals, so alpha x1 of t plus beta x2 of t, so two signals weighted with some coefficients, the system should be linear with respect to those sums and coefficients. It should be equal to alpha phi of x1 t plus beta phi of x2 t. So we should be able to take the constants out and any linear combination, so that the response to the sum of signals should be equal to the sum of individual responses. So this is linearity. The second condition that I would like to impose is that the system does not have a long memory. Yeah, so if we come back tomorrow and we repeat the experiment, we should get identically the same answer. In formal language, that would be time translation invariance. That is, if we send into the box a signal that's shifted in time, so x of t minus t0 by some t0, the output of the box should similarly just be shifted in time, but otherwise should remain the same. So it must be the same as y t minus t0, where y of t is a response to just x of t. So that's linearity, that is time invariance, and you can probably guess from your physical intuition that bells mostly satisfy. That is, if the knock is sufficiently weak, then two simultaneous knocks on it will just produce the linear combination of responses. And if we hit the bell tomorrow, we'll get the same ringing from it as we did today, assuming that we don't hit it very hard. So this LTI assumption generally holds for relatively weak perturbations, because if we smack it really hard, we're just going to crack the bell. Right. So let's now explore the consequences of this and explore how it relates to Fourier transforms. So we've got these input signals, we got the output signals, and to fully characterize our linear time invariant system, we could perhaps compile a library of various inputs and the corresponding outputs. And they're just functions of time, and as you know from your basic mathematics, a good library of functions is just a set of orthonormal functions called a basis. So why don't we fix the basis set and just look at the responses. So let a set G K of T be the basis. of functions which are orthogonal under some scalar product. We don't need to specify at the moment what that is. So of orthonormal functions. Then any particular function, and we'll call this x, then any x of t would have an expansion in the basis. So it would be a sum of k, chi, k, where chi has the coefficients, g, k of t. So for those of you who haven't encountered much functional analysis, it's the same as what we've got in the vector calculus. So if g's are a bunch of vectors, and x is a particular vector, it would have an expansion in g's. It's just in our case, g is a particularly long vector, and the number of elements in it is in fact a continuum. But other than that, it is quite similar. So then chi of chi k, the coefficient, will just come out of the scalar product of x with the g. So how many of you have come across Dirac's notations by now? So most of you, somewhere in some courses. So it will be g k of t applied to x of t. Or if we choose a particular scalar product, so just the usual Hilbert space scalar product, it's an integral from minus infinity to infinity, g k complex conjugate if it's complex, t x of t dt. And k is integer. Right. Now, what we could also do is expand the x, not in terms of a discrete set of functions, but in terms of a continuous set of functions. So via an integral transformation. So it's very similar, it's just the index k is assumed to be continuous, in which case the sum mutates into an integral, and so what we've got instead is x of t would be an integral from minus infinity to infinity, chi of tau, g tau, t d tau. So you can see the similarity. We've just taken the index k and it became a variable. And we're no longer summing but integrating over it. And in this case, g is called the kernel that transforms these coefficients into the actual signal. So, okay, that's our library. So now let's take a look at the effect that our linear time invariant system would have on such a signal. So, phi acting on x. So if we substitute this expression for x, what will happen is we will have a sum over k. Remember that phi is linear. So phi k phi g k of t. Now you can see the interesting conclusion here is that in order to predict the system response to any function whatsoever, it is sufficient to know its responses to basis functions. Okay? Then we just combine those responses with the same coefficients and we get the resulting answer. And similarly, we can do it in the integral representation. So phi x of t would in this case be an integral chi of tau and then the response of the system to g tau and t d tau. Okay, so the responses to basis functions therefore define our linear time invariant system completely, because the only thing we need to know is how it responds to the input that we put into there. Okay, so we've worked out this much. Now let us try and work out the response of this LTI system to the hammer. So what is a hammer? A hammer is an infinitely sharp strike with a finite energy. So can you think of a function to represent such a thing with? Delta function. Perfect. So let's stick a delta function in and let's see what happens. So From your analysis course, we know the following about the delta function. In fact, that is actually the definition. It's not, strictly speaking, function. It's a functional. It's an operator that maps the Hilbert space of all functions into the field of numbers. So f of x naught at a particular point is equal to integral from minus infinity to infinity f of x delta x minus x naught dx. This, in fact, is the definition of a delta function. It maps the space of functions into a field of numbers. So let us now express our signal in this same way. So we can say that x of t will be an integral from minus infinity to infinity x of some tau, then delta t minus tau, or tau minus t, it should be t tau. Okay, but to this we can actually apply that. Yeah? So let's now figure out the response. So phi to x of t will be a phi applied to this. So we will now use this equation, and that will be equal to, should get some board. More convenient. There we are. So as per this relation here and this relation here, what we've got is an integral from minus infinity to infinity x of tau phi of delta tau minus t. Of course, that's the only thing that depends on time. The delta function, tau is a parameter, t tau. Now, it so happens that this has a special name. It's called h of t minus tau, and that is a pulse response. And so h of t is phi of delta of t. That's a response to the hammer. But you see what happens. It turns out that this hammer response also defines the system completely. So if we do know h, then the convolution integral of h with any input signal will define the output signal. So it turns out that the response to a hammer strike has a fairly special status for a linear time invariant system, in that the knowledge of that response completely defines the response of the system to any possible input. And so finally what we get out of this is the so-called convolution integral. So phi applied to any signal x of t is equal to the convolution of that signal with the pulse response. Infinity to infinity, x of tau, h of tau minus t, d tau. So in the trade, such an integral is known as convolution integrals. Okay, so we have now worked out the response of the system to the hammer strike and arrived at something fairly non-trivial. So why don't we now take a look at the response of the system to a continuous frequency. And then we will discover that we can actually relate the two, and that provides the foundation for the whole of Fourier spectroscopy. Okay, so frequency response. So why don't we take our system and feed a frequency into it? The most general function that has oscillatory behavior is a complex exponential. So in quantum mechanics we work over complex fields, of course, so we need to worry about things possibly being complex. So what I'll feed in is just one such complex exponential. It will be phi of ei omega t. Well, as per the derivation that we did above, we need to take a convolution of this function with the pulse response. So it will be an integral from minus infinity to infinity e I omega tau h of tau minus t t, tau. I'll do a bit of a variable substitution. You can see we are integrating over tau. So I'll multiply and divide the whole thing by I omega t, just to bring the variables into agreement. So it will be e plus I omega t, then integral minus infinity to infinity, e I omega tau minus t. So that's the minus part of that. So 1, and then h of t minus tau minus t, d tau. Now, because the integration limits are infinite, we can shift it arbitrarily by a constant without affecting the value of the integral, and so that is e I omega t, integral from minus infinity to infinity, h of tau e I omega tau d tau. Now, who recognizes the operation? Fourier transform. So it has started cropping. So we will designate the Fourier transform of the pulse response with the capital H. So it will be h of omega, the Fourier transform is a function of omega, times the original frequency. So you see, it turns out that a linear time invariant system does not permute frequencies. Whatever you are shining on it will be multiplied by some number. The actual number will depend on the properties of the system, but it will remain the same frequency. Okay, so that's the first path that we took through it. We arrived at the Fourier transform. Okay, so that's the frequency response. Now, on the other hand, what we had in here is that to get a response to any input, including the oscillatory input, we need to take the convolution with the pulse response. But the frequency response from this is a Fourier transform of the pulse response. And so we are arriving by coming from these two sides to a fairly fundamental relation, which states that the frequency response of a linear time invariant system is equal to the Fourier transform of its pulse response. So finally, the take-home message, h omega is integral minus infinity to infinity, h of tau e I omega tau d tau. And that is the foundation of all Fourier spectroscopy. So we could shine every frequency in turn and record h of omega, or we could hit it with a pulse and record h of tau and then Fourier transform, and fundamentally, so long as the system is linear time invariant, we should obtain the same answer. So in the context of NMR spectroscopy, the pulse response is known as the free induction decay. It usually has some kind of shape like this. When you give it a pulse and then you record the magnetic field the system produces with an electromagnetic coil, and then a Fourier transform of this, ft, will produce what is known in the trade as an NMR spectrum. It is a collection of sharp signals corresponding to the frequency components of the original oscillator. So this is, as it were, the casus belli for the presence of Fourier transform in quite a few spectroscopies. You will see that in the infrared, you will increasingly see it in the optical spectroscopy these days, certainly in NMR and EPR spectroscopy, and well, almost anywhere where the acoustics is involved. So what we will proceed to do now is to study the properties of the Fourier transform, because they then determine, on the one hand, our strategies for processing experimental data, It is often possible, by very careful application of digital signal processing techniques, to turn completely hopelessly noisy data into a beautiful collection of resolved signals. On the other hand, it's possible to turn a beautiful collection of signals into a noisy bump if you misapply those digital signal processing techniques. So on the one hand, we'll know better how to process these things. On the other, we will also know better how to simulate these things. Because when you come to the Schrödinger equation, you could either diagonalize your Hamiltonian and obtain the frequencies, in which case you're working in the frequency representation, or you could run the time-dependent Schrödinger equation forward in time, record the dynamics of the observable. That would be the pulse response after some pulse that's applied to it, and then Fourier transform the dynamics. Those are, as per this, equivalent ways of doing it, but these days we mostly gravitate towards the time domain simulation, whereas I understand computational chemistry people actually gravitate towards the Hamiltonian eigensystem simulation. So,
is the one that you work in the Liouvillean space and the other one's the Hilbert space?
No, we'll get to that by about lecture 3. Both Hilbert and Liouville space simulations in NMR are generally time domain. Liouville space is the joint representation of the Hilbert space. But the frequency domain simulations are indeed much more convenient in Hilbert space. And quite a few things like the treatment of relaxation is not in fact possible in the frequency domain. Or is difficult because various matrices are singular and non-Hermitian. Right, so the properties of the Fourier transform. There are two Fourier transforms out there. One is called the forward one, the F plus, and the other the backward one, the F minus. Now, before I even draw those formulas, I might save you considerable time by saying that conventions differ. I will now put certain coefficients in front, which ensure that the transform stays unitary in the mathematical sense, that it is preserving the functional norm. Engineers, unfortunately, didn't appreciate the beauty of mathematics, and they have these coefficients the different way around. Applied mathematicians have got them an even more different way around, and then somebody came and generalized it all into some huge coefficient in front of it, and it became even less comprehensible. Anyway, if you stick to the definitions that I give, you'd be fine in magnetic resonance, and you'd be fine in most things which do worry about the mathematical properties of the system, rather than how well it sells. So the transformation that I give you is the unitary transformation. So of F of t is 1 over root 2 pi. This is where we and the engineers differ. Minus infinity to infinity, f of t e minus I from t dt. And the f minus, the backward Fourier transform applied to f of t is 1 over root 2 pi. It's the same coefficients, so they're mirrors of each other. Minus infinity to infinity, f of t e plus I from t. Now, they are called forward and backward Fourier transform because they happen to be each other's inverse. So if you apply the forward Fourier from here to here, and then the backward Fourier to this, you'll get the original oscillation. And what's important, the map is what's called mutually unique. That is for well-behaved functions. And the function has to be exotic indeed not to have a Fourier transform. These mappings are one-to-one, so you don't lose any information by applying the Fourier transform. But what we'll now prove is that they indeed are each other's inverse. And for that, we would need to remember one of the definitions of the delta function. Again, this is not a mathematics class, so I'll just give it to you. Delta, one of the many definitions of the delta function is the following. It's the principal value of this integral I omega t d. And principal value means that when we plug, when we take the integral and apply the limits, we apply them symmetrically, otherwise the integral doesn't exist. Obviously, it's an integral of a non-decaying oscillatory function. So this is delta function, and we will now use this fact in our proof. So let's apply first the inverse Fourier transform to some function, f of t, and then apply a forward Fourier transform to the result, f plus, and see whether or not we recover the original function as a result. So 1 over 2 pi, so I have collected a pair of these roots in front, integral minus infinity to infinity of another integral minus infinity to infinity f of t prime e I omega t prime dt prime. So that is the inner inverse Fourier transform. The resulting function would be the function of omega, so the forward transform has to operate on omega. So what we will have is e minus I omega t but d omega. So well, we now need to reshuffle a few things here. It will be 1 over 2 pi integral minus infinity to infinity f of t prime dt prime, and I'll collect the two exponentials together, an integral minus infinity to infinity e I omega t prime minus t omega. Now you see it's a chained integral. Here we need to take the inner one first, then put it into the outer one, and take the outer one. But I can use this property of the delta function here to make it into a delta function. So what I've got therefore is 1 over 2 pi. It also cancels because of this. And so we are left with the integral minus infinity to infinity f of t prime delta t prime minus t dt prime. And from this, I just need to use the property of the delta function, that it simply returns us the value of the function at the point of this constant. And so that's it. So that's the proof that the two Fourier transforms are each other's inverse. It's a useful exercise at home to just swap the plus and the minus around and to demonstrate that it also works correctly the other way around. Right, so that's the first property. The next property that we need to prove, which probably doesn't even require a proof, is that the Fourier transform is linear. Well, there's not much to prove there, really. You know that integration operation is linear, that we can take constants out of the integral, and that the sum or difference under the integral is just a sum or difference of the corresponding integrals. So the linearity, which is there in your equation 15, I would not even prove. Now, property 3 in your handout is the fact that the Fourier transform of a derivative is related to the Fourier transform of the original function. And if it's a very high derivative, that can in many cases matter a great deal. Many of you had courses in ordinary differential equations. You may remember those fairly nightmarish solutions with variations of multiple constants in there, and plugging things backwards and forwards and the initial conditions and so on. That nightmare is largely avoided if you solve those systems with Fourier transforms. And in many cases in magnetic resonance spectroscopy, it is faster, computationally cheaper, and more convenient to solve directly for the Fourier transform by applying it analytically to the equations before you even run the simulation. So this is another property which I feel I should prove explicitly on this board. I mean, more generally, I mean, I could have just dumped all these properties on you and told you to get on with it, but sort of these two boards, they represent the Russian school of doing things, where we derive things and explain them properly. And I find in practice that this works considerably better than just loading you with a bunch of PowerPoints that don't give much explanation. You just run through them at a great pace. So let's now prove the relationship between the Fourier transform of a derivative and the Fourier transform of the function. Now, in your handout, the derivation is given in full generality for kth derivative, and it relates it to the k minus 1th derivative, but really that's a bit too general even for the board, so what I'll do is I'll just derive the Fourier transform of the first derivative, and you can work by induction from there. So, let's say we've got f plus applied to f prime of t, otherwise known as df by dt. So, 1 over root 2 pi integral minus infinity to infinity f prime of t e minus I on t dt. Let us integrate this by parts, as we usually do when we have some straightforward derivatives under the integral. So I will remind you what integration by parts is. If you have an integral u dv, it's uv in the same limits minus the integral v du. I think that's right. And so in our case, u would be e minus I omega t. du, differential, would be minus I omega e minus I omega t dt. dv would be f prime of t dt, and e therefore would be just f of t. And so we plug that into this expression. So uv, so that is f of t e minus I omega t from minus infinity to infinity, then minus an integral v du. So that's the v and that's the du, and you can see the derivative disappear. So minus and minus is a plus. So plus I omega integral from minus infinity to infinity e v du, so f of t e minus I omega t dt. Right, so you can see we have popped out something in front, and here we actually have the Fourier transform of the original function. Now, it so happens that in this particular case, the infinite integration limits would cause us difficulty, because we don't really know anything about f. We don't know whether this expression, therefore, would ever have a defined value. Yeah? At minus infinity to infinity, some oscillatory processes might not actually have a defined value. So what I'll drop down to here, therefore, is the Fourier transform that we use in systems which have causality, yeah? Where the system's future cannot affect its past. And so the integration, in fact, happens not from minus infinity, but from the moment when the system's evolution has started. And that's a defined moment, and which is conventionally put to 0. In which case, that's a physical assumption, of course, that I'm making. It has no mathematical justification here. For causal systems, we can continue this derivation. Right, so at the infinity, we assume that all dynamics in the system just decays. So f of infinity is 0, it has reached some kind of equilibrium. And at 0, we just have f of 0, and the same is just stays here there. So we have f of infinity e minus I infinity omega minus f of 0 plus I omega, and this is the Fourier transform, so it's the f plus of f of t. So what we now have, therefore, is the following: minus I omega f plus of f of t minus f of 0. And you would notice that the first derivative would of course occur in the various ordinary differential equations. And one thing that we do essentially require to solve an ordinary differential equation is the initial condition, and which is f of 0. And so this initial condition will naturally pop out in our derivation. And so the solution by a Fourier transform is not something magical, it's just a reformulation of the ordinary ways of solving them. Okay, so in the case that's given in the handout, things are done with proper justification for minus infinity and infinity. Here, I did a bit of a fudge to simplify the board derivation, and it is given for the case derivative rather than just the first derivative that I got. Right. The next property, which we will find extremely useful in the next lecture, in lecture 2, is the convolution theorem, which relates Fourier transforms of convolutions to Fourier transforms of the original functions. And convolution operation occurs a lot in things like radio astronomy, digital signal processing in acoustics, as we'll see in the next lecture in magnetic resonance spectroscopy. And it's a pretty expensive integral. So if you look at what convolution is and how it is defined, f convolution g is defined as the following integral. Integral minus infinity to infinity f of tau g of t minus tau d tau. And if these functions are large, if they occupy significant chunks of the whatever space that tau lives in, and it's an integral that's indefinite, so one might conceivably have to integrate it for a hell of a long range. So this is a very inconvenient definition from the computational perspective. And so it would be really nice if we could convert it into something that is in practice more computable. And just as the case was in the differential equations, Fourier transformation comes to help. And it turns out that if we Fourier transform these functions individually, so f plus of f of t and f plus of g of t, if we then just multiply these Fourier transforms and take the inverse Fourier transform of the result, it just happens to be equal to that convolution. Now, not a trivial statement to make, but you can see how it can be extremely useful. Fourier transforms can be performed really fast. All of you have heard of the so-called fast Fourier transform algorithm, which is responsible in particular for, I guess, on the modern music centers, do they still have those jumping bars? You know, at the bass and the high frequencies and so on. So those jumping bars are in fact the Fourier transform of the signal that goes through the headphones. And it can be computed really fast because extremely fast algorithms exist, almost linear time algorithms for the calculation of Fourier transforms. Whereas this integral is likely to be quadratic time in the number of in the storage that's required for the f. So it turns out, because of the existence of this fast Fourier transform, that this is really useful. And it will be useful to us in the next lecture when we use signal processing. So why don't we prove that thing properly? though maybe not. I mean, it's half a page even in my handout, and it's 6 equations. So if you look on page, it is page 3 of your handout, equations 21, 22, 23, 24, and 25. You would perhaps forgive me for not copying it on the board. I've got enough to be going on with. Now, one particular corollary is the Wiener-Hintgens theorem, which is useful for evaluating correlation functions, in particular autocorrelation functions. So in statistics, an autocorrelation function is the following. It's f star of tau, f of t plus tau d tau, and it just happens to be as a corollary of this equal to f plus of the modulus of f minus f of t squared. So those of you who do molecular dynamics simulations and process MD trajectories will often need to extract correlation functions for molecular motion, and this is how in practice they are extracted, because the original integral would have been a much more expensive thing to compute. Right, the next property is fairly trivial. It is number 6. It simply says that when we shift the time of the original function, the result is, when you take a Fourier transform, the modulation of that Fourier transform. So complex exponential pops out in front is a one-line proof. So I wouldn't stop on that. Now, what's more important is the proof in equation 29 that the Fourier transform as we have defined it is a unitary operator. In quantum mechanics, unitary operators are the ones that preserve the total probability. And as you know, for wave functions, the normalization is critically important. And so that one actually merits proper proof. And then you can go and use it in quantum mechanics with your heart put at rest. The transform is indeed unitary. Right, so to prove that it's unitary, we need to just show that the norm of the function doesn't change, and the norm of the function, f of t, at least the standard 2 norm for it, is the square root of the integral minus infinity to infinity, f conjugate of t, f of t dt. So we just need to demonstrate that the square of the norm doesn't change, and that will do. So the square of the norm is that integral, so minus infinity to infinity, absolute f plus of f of t square d omega. Remember, the Fourier transform is a function of frequency. So f star f is just the absolute square of the function, and we applied that to the Fourier transform. So we now need to demonstrate that this is in fact equal to that. And let's just do it. So it will be an integral from minus infinity to infinity of 1 over root 2 pi integral minus infinity to infinity f of t e minus I omega t. That's that integral once. So that's the f. Let's now do the f star. Another integral minus infinity to infinity. 1 over root 2 pi in front. F conjugate of t prime here everywhere. Should it? Just if you could put a prime at the end of the first line of equation 29, the last dt should have a prime. Doesn't really matter here which variable I use. E plus I omega t prime dt prime. And the result is d omega. So what I'll do is I'll just make sure that the integration variables on the two integrals are different. So I'll remove the prime from this t, and I'll merge the integrands together. So what we'll have from this is 1 over 2 pi integral minus infinity to infinity with respect to t, dt integral minus infinity to infinity with respect to t prime, and then it all integrates the following thing: f of t, f conjugate of t prime, integral minus infinity to infinity, that's that integral that I migrated in, e minus I omega t minus t prime, d omega. Right, you can see we got a delta function here, yeah, from that same definition that I previously used, and when we use it, it's going to eat our 1 over 2 pi. So that means we got the following: integral minus infinity to infinity dt integral minus infinity to infinity dt prime, integrating f of t, f conjugate of t prime, delta t prime minus t, and this would only integrate to something that's non-zero if t equals to t prime, as per the properties of the delta function, and that will eat our integral as well. So the result is integral minus infinity to infinity f of t, f star of t, so t equals to t prime, dt, and that is exactly that definition of the norm. So that's the norm ft squared, and the original thing was the norm of f omega squared. So you can see the norm is preserved by the forward Fourier transform, and a similar proof will convince you that the norm is preserved by the inverse Fourier transform. Right, so the rest of your handout, there's a paragraph there on the fast Fourier transform. In practice, what we have when we've recorded the signal is not, of course, a continuous function which we could integrate. Yeah, integration is an analytical operation, and we never get a sine or cosine analytically out of the instrument. It's always a table of numbers, which may or may not be sine and cosine, but what we need to do in practice is to integrate it numerically. Now, when we do it numerically on a sufficiently fine grid, the integral is replaced by a sum, and that was the original way to define the integral, so-called Riemann sum. And in fact, the symbol of the integral is just a stretched s, which originally stood for summation. And so the discrete version of a Fourier transform for a signal which is only digitized in a given number of points will be formulated not in terms of functions of a continuous variable, but a vectors enumerated by a discrete index. So f plus or minus applied to some vector f will essentially be a matrix operation. 1 over n, where n is the number of elements, root 2 pi. Instead of an integral, we have a sum, k, from 0 to n minus 1, or from 1 to n, depending on how you number your numbers. F, kth component, e plus or minus plus here, to be consistent. I, k, and omega n. So if you look at how it relates to the usual analytical Fourier transform, you can see that f of t became fk, so it's now a discrete vector. E minus I omega t became e I k m divided by the length of the interval, so this also has the correct relationship between the frequency and the time, and we are taking the discrete sum. Now, typically, you see what this would require us from the computational perspective, so that's the nth element of the resulting vector, is for each element of the Fourier transform, we would need to do n multiplications and n exponentiation operations. Now, these exponentials can be kept in a computer memory as a table, only computed once, so we don't really need to recompute the exponential every time. But at the very least, we will have n multiplications here, where n is the total length of the data set, for each element of the Fourier transform. And there are n elements in the Fourier transform, so the cost of the operation is n squared multiplications in a computer. So typically double precision floating point operations. So the cost of a naive Fourier transform, therefore, is quadratic in the size of the data you're transforming. Now that matters because we can record several million points in one go. And several million squared is a hell of a lot of multiplications. Even the modern computers will struggle with that much. And in 1960s, when Fourier spectroscopy started to emerge, this was an absolute non-starter. And even the early NMR work suffered a great deal. All of you will sooner or later come to NMR conferences where the old-timers like Richard Ernst like to tell the stories about how they adjusted the phases of their spectra in the 1960s and 1970s. They would punch it on tape or record it onto a magnetic disk and take a taxi to the supercomputing center. The following morning, the Fourier transform would be ready. They'd realize they haven't got the phase quite right. They'll work out the correction to the phase, repunch their tapes, take a taxi to the supercomputing center. The following morning, they get the spectrum. Now, the fact that you can actually phase it with a mouse in real time on modern instruments is down to the fact that two amazing guys, Cooley and Tukey, I think the names are, have worked out a much more efficient way of doing the so-called fast Fourier transform, which accomplishes the same in the order of n log n mathematical operation, by carefully subdividing the intervals and taking advantage of various intermediate results in storage. I wouldn't go into the depths of how that's computed, but it's a much, much faster process. Logarithm is a very small function, so essentially it's a constant for reasonable values of n, plus or minus, and so this is linear cost. So if we have a million points in the data set, the number of multiplications that we need is a million times log a million. Log a million is what? Log 2 of a million is about 20. And so 20 million multiplications is a triviality. A modern computer will do it in less than a second. And so this is why you can phase those spectra in real time and process them. It's the existence of this fast Fourier transform. Okay, and we'll get through the applications of all of that to real life NMR and EPR data processing in the next lecture. So today was the really hardcore mathematics. Next couple of lectures will be mostly physical things, and then the amount of mathematics will just be out of all scale. So then we'll hit the real quantum mechanics of things. It will get even worse than that, so come prepared. Okay, so the handouts have evolved over the last few years into pretty readable stuff. So do make sure you understand the previous lectures before you turn up to the next ones. Any questions?